In this video, we will be discussing about what is the power factor, why it is being very much important in the case of electric circuits. So first we will see a small recap. So considering our sine wave, so obviously we are synthesizing instantaneous power. So instantaneous power P of t is given by the equation voltage into current, which is varying based on the time. So it is very T mentioned the time. So if you see the graph, the voltage and current vary instantaneously based on the time value. So Vm and Im are being measured and both has a different type of angles. So the power in AC circuit is not obviously flat or constant. It obviously changes based on the time and the rate of change of energy which is being transferred from one form of energy to another form. So the P of T, that the power is being given by the equation Vm, where Vm is the maximum voltage and Im is the maximum current, divided by 2 into cos phi minus cos of 2 omega 2 minus phi. Here where the average power is an oscillation term. Okay, so phi is the oscillation term over here. The three phases of AC powers are three important factors of power in case of AC circuits are average power, reactive power and apparent power. So what is meant by average power? The average power or the real power is the actual work done by the resistive components. Okay. So what is the amount of actual work which is being done by the particular circuits? So which is given by the equation, we can measure the actual power using the actual power is being denoted by P. The value of P can be measured using the formula Vrms into Irms into cos phi. Since here we will be considering only the actual work done, the oscillation part is being omitted. So Vrms, Irms is nothing but the root mean square value of voltage and the current. Next comes our reactive power Q. Reactive power is something that it does not relate with the work done. It is something that the amount of power is just being stored and released by the inductor and the conductors. It does not give the actual power and it does not do any useful work. Okay, it's just simply store and release the powers. That's it. So which is denoted by Q. The value of Q can be obtained using the formula Vrms into Irms into sin phi. Okay. Next is the apparent power. The apparent power is denoted by S, which is the total power flow supplied to the circuit. It's just the power flow which is being given throughout the circuit. That's it. So it is denoted by S, which is given as the product of Vrms into Irms. So when we coming for measurement unit, the average power is measured with watts and reactive power is measured with volt amps reactive and S is measured as volt amps. These three are the main factors in case of power factor. So next comes our hero, which is the power triangle. So this is the power triangle, which is the angle is indicated as psi. By using the Pythagoras theorem, this is a right angle triangle, so we will be using the Pythagoras theorem. Using the Pythagoras theorem, A square, the apparent power, can be equated to the real power plus the reactive power. So A square is equal to P square plus Q square. So the base will be the real power, perpendicular is the reactive power and hypotenuse is the apparent power. The angle between these apparent power and the real power is the physical relation or the phase difference between the system voltage and the current. Okay. So how the power factor comes into role of efficiency matrix. So the power factor of a particular circuit or anything can be measured using the formula as the ratio of the real power to the apparent power. Okay, so the cos phi is nothing but power factor is equal to cos phi. The cos phi is nothing but the ratio of the real power to the apparent power. So we already discussed the real power is the actual amount of the work done, where apparent power is something that the amount of power which is being supplied to these circuits. Okay. So the in case of why the power factor is more important is that when we have a high power factor, then obviously your system is very much effective, which indicates the energy loss is very minimal. So the in ideal state, P divided by S, that ratio will be equal to 1, which means 100% of power is being effectively used for real work. So it is structurally equal to a purely resistive load. So diagnosing the inefficiency, which inefficiency can be measured, it may be lagging or leading power factor. So lagging power factor is something that when the current arrives after the voltage. So where it occurs is that in highly inductive industrial loads such as large electric motors or transformers, when these type of scenario occurs, the scenario is that the current lags by the voltage by the value of phi. Okay, so the current arrives after the voltage. Leading power is something that current arrives before the voltage. So when your circuit has a heavy capacitor load or capacitor bank kind of things or substation routings, etc., the current will be leading the voltage. Okay, these are the two scenarios where the inefficiency will take place in case of power factor. One is lagging power factor, another one is leading power factor. So when we are considering the load environments, based on the load only, we have discussed that our power factor will be there. We have three types of load environment: resistive, inductive and capacitive. In case of resistive load, the current and the voltage are perfectly in phase. So the power is always positive and the energy consumed will be very high. In case of inductive load, the current lags the voltage. So powers alternate between positive and negative. When we take the average value, it will be 0. In case of capacitive load, the current leads the voltage. Power is similar to the inductive load. The power alternates between positive and negative, and the average power will be equal to 0. So no net energy consumption will be there. So coming to the real world impact of low power factor, let me consider a problem: grid strain. So when excess current load is being applied, then there will be a severe thermal loss as shown in the figure. The amount of apparent power to accomplish a small amount of real work itself, there will be a severe thermal loss. So what will happen? It will result in a high current requiring for a thick transmission line. Okay, so we are using a thick transmission line in case of our grid systems. So when the low power forces the grid to have a severe thermal losses. So what is the solution for this is, apparently we will be using a capacitor bank. So where we will be just loading the capacitor where into a motor heavy systems, so the reactive power get cancelled, pulling the system back towards perfect unit power factor. So the solution for power factor correction is using the capacitor bank. So what are the future scopes where in the smart grids, when we are integrating our AI system, what we can do? So the AC power should remain constant. In case of shifting from one grid station to the another, the software driven management can be used, and the real time phase analysis and power factor monitoring can be introduced in order to predict the and also we can use a predictive maintenance algorithm for load balancing. So the dynamic automatic power correction will use to stabilize the grid and maximize the maximum amount of energy efficiently without any human intervention. So in our future scope, when we are integrating our AI with the smart grids, with these following factors, we can achieve a high power factor value. So this is the equations which we have seen already. This is a just recap of what we have seen. The instantaneous power can be given by as the product of the voltage and the current, which is varying with the time, and power geometry, that is our power factor triangle, is given as a square equal to p square into q square, and real power is something that P is equal to product of VRMS into IRMS into cos phi. Our power factor is nothing but the ratio of P and S. Hope in this video you would have understood what is meant by power factor, why the power factor plays a major role in case of our electric circuits, and how using our A integration we can reduce the low power factor and increase the efficiency of transmission. Thank you.